arriver au fur et à mesure.
Mm-hmm.
Eh bien, écoute, d'abord, merci d'être avec nous aujourd'hui après cette folle semaine de SF2A où tu as déjà parlé. Donc, juste un petit mot, tu es en poste au LAM hein, à Marseille, où tu t'intéresses aux galaxies depuis longtemps d'ailleurs, hein, et en particulier à la formation d'étoiles dans les galaxies. Et aujourd'hui, donc, tu vas nous parler de nouvelles techniques pour retrouver les galaxies sur la séquence principale, si je me souviens bien.
Oui, oui.
Donc, on t'écoute et puis voilà, merci beaucoup en tout cas.
Okay. Thank you very much first for inviting me to give this seminar. I'm very happy to show this new study because it's something quite recent that we are developing at LAM. First, we had to, we are astronomers and we are not at LAM in our team, and we are not very familiar yet with the machine learning techniques. So we asked for the help of statisticians that are our neighbor in terms of laboratory. So from the Institute of Mathematics de Marseille. So it's a joint collaboration with mathematicians and astronomers. So, and the machine learning part of the study has been done mostly by Grégoire Aufort, who is a PhD student in both astrophysics and statistics. So it's very a joint effort from both laboratories. So the outline of the talk, first I would like to present the question I want to answer and why we decided to use the machine learning approach I will present. Why did we need this kind of improvement compared to our previous study? I will then show the machine learning approach and the application on real data. And then I will try to show other studies that I found in the literature that aim at doing this kind of research, which is constraining the star formation history of the galaxy from machine learning. So it's something recent, but there is a couple of studies that I could show in comparison. So first, what is the question I want to answer? So in extragalactic astrophysics now, it's now admitted that there is a quite tight relation between the star formation rate of the galaxy and the stellar mass of the galaxies. So this relation is called the main sequence. This is what you can see in blue. And above the main sequence, you have a relatively constant over the cosmic time and the stellar mass. So what is the origin of this scatter and how can we explain it? So there is now some things that are admitted. It should be linked to the star formation history of the galaxy, but is it due to short-term stochasticity? So something associated with the self-regulation of star formation activity, and we are talking about timescales of the order of 0.2 to 2 gigayear. Or is it something due to differences in the long-term star formation history of the galaxies and something linked to the initial condition of the dark matter halo of the galaxies? So this is one of the key questions. And to try to answer that, I would like to follow the movement of the galaxy within the scatter on the star formation rate stellar mass diagram. So to do that, I need to probe quick movement, things like you can see on the right figure. So I want to see different paths, distinguish between different paths that the galaxy would follow on the stellar mass, star formation rate, stellar mass main sequence. You can imagine first that in blue, the path in blue that you can see that the galaxy grows smoothly, gain mass, and then at some point stop forming stars and then become passive. You can imagine, on the other hand, like the red path, that the galaxy is normally forming stars, and at some point it becomes a starburst, and then at the end of the starburst, maybe the gas is all consumed and the galaxy goes down in the passive region and stop forming stars. Or you have another possibility that the galaxy have this kind of movement in green that you can see, where it's still in the scatter of the relation, but they have some movement going up and down, and at some point it stops forming stars and become passive. And finally, we can expect to have some passive galaxy that after a minor merger or something restart to form star and could go back to the main sequence. So what I want is to distinguish between all these evolutionary paths. So these are short time scale movements. So below 100 mega years, this could be due to the formation and destruction of a giant molecular cloud. And in the intermediate scale, so 100 mega year to 1 giga year, you have many mechanisms that could produce this kind of variation in star formation activity. You can have galaxy mergers, disk instabilities, bar-induced flow, environmental effects, etc. So in an ideal world, what you would do to probe this different scenario is to look at the spectroscopy and especially some indication of a star formation history, such as the Balmer lines or the Balmer break. All this information coded in the spectra. Unfortunately, we don't have many spectra. For example, in the cosmos, we only have a spectroscopy for 1% of the whole sample. And since we are dealing with very short and very quick movement, we need a lot of statistics to pinpoint the galaxy while they are undergoing this kind of variation. So the need for the statistics make that we have to find a method that is efficient and that use broadband photometry, which is what we have for most of the galaxy in extragalactic astrophysics. So since it's a machine learning seminar, I wanted to highlight some method that have been published to measure the stellar mass and the star formation rate of the galaxy, because they are the endpoint of the star formation history. So if I want to be able to recover the star formation history, I need to have a very reliable measure of the stellar mass and the star formation rate. So usually in a traditional or classical way, what we do is that the stellar mass is probed by the near-infrared part of the spectral energy distribution of the galaxy, and star formation rate is measured from UV or for infrared, or best the combination of the two. So what also is done usually is that we perform SCD modeling, but these are, of course, there are assumptions on the star formation history, the attenuation, and the infrared emission of your galaxy. So very recently, so you can see that these articles are from 2019 and later. So now people are trying to use machine learning to measure the star formation rate and the stellar mass in some methods that are model independent or based on simulation from cosmological hydrodynamical simulation like Eagle or Illustris. So here is just some example. So on the left, you can see the study that focused on the infrared luminosity of the galaxy. So there, the author used a shallow neural network to predict the infrared part of the SCD of the galaxies from the UV to near infrared. So this is something quite new, and they managed to recover quite well the dust luminosity of the galaxy. In the middle, using random forest, Bonjean et al. Tried to recover the stellar mass and the star formation rate of the galaxies. You can see the stellar mass works quite well. Star formation rate is a bit more dispersed, but still, this is something interesting and promising. And then on the right part, from deep neural networks, Rana et al. Here also try to recover the stellar mass and the star formation rate. So this is an active field in terms of measuring the properties. Here, I will use the classical traditional SCD modeling as a base of a base framework for my study. The reason is because we are very familiar with SCD modeling now, and we quite understand the biases that we have. And also, I will use a model of star formation history that allows me to come back a bit in time. So I will explain this more later. So here I need to use SCD modeling, but all this machine learning approaches to measure the physical properties of the galaxy are, of course, a next step for the kind of study I want to perform. So here I go to the machine learning approach that we use. So to understand that, when you do SED modeling, you have to assume mostly you have to assume a simple modeling of the star formation history. So what people use usually is something very simple, like an exponentially declining SFH, like you can see in green or in black, or a tau delayed SFH, which is the one you can see in purple. And on this simulation, which is the top panel figure, you can see that the tau delayed SFH recovers quite well the long-term star formation history of the galaxy. But if you look at the end, so at 6 giga-year, you can see that from the simulation, which is the gray line, we are quite off compared to if we want to measure a star formation rate. So we need to be a bit more accurate to recover the star formation rate. So you can see in the bottom, the two bottom figures on the left, if you use the tau delayed star formation history, and you look at this famous star formation rate versus stellar mass relation, the other drawback of the tau delayed star formation history is that it creates a kind of a artificial gradient in terms of age. You see that this kind of rainbow, which is actually artificial. So what we need now, what we think we did to overcome this problem is to use a flexibility. So when I say a flexibility, is that in the recent star formation history, so the last 500 mega years, we allow the code to increase or decrease the star formation rate. So we add this flexibility, which is handled through the parameter that I define here because I will use it a lot, the RSFR parameter, which is the SFR now divided by the SFR before the flexibility. That could be a quenching or a starburst. So now with my machine learning approach, I want to answer the question, is this additional flexibility needed to model all galaxies SFH? And what are the galaxies that need this flexibility and why? And they are, for me, the most interesting in galaxies because it would mean that they have recent, less than 500 megayears, and strong movement of their star formation activity, which is exactly what I want to probe on the stellar mass star formation rate diagram. So we use the approximate Bayesian computation, which is called ABC. So ABC is used in many different topics. So I just listed a few of them just to show that there are different application. So it was used in genetics of population, both humans or insects, insects too. So you can find different studies in the literature. I found some application in the calibration of image simulation for cosmological surveys. There is the paper of our student Grégoire Aufort, which is the study I'm presenting now. And also very recently, there was some measurement of narrowband galaxy properties using the ABC method. So the thing is very simple. So you start with a set of parameters, which is theta here, and you build your model with your set of parameters. Here, your model M would be the SED, the spectral energy distribution of your galaxy, which is the emission, the flux as a function of the wavelength for your galaxy. So you compute your flux in different bands from your model. And then you compare this simulation, which are the red points, to the actual measurement that you have for your galaxy, which is the blue point. You calculate the distance between them and you reject or not the model depending on this gamma parameter. This is actually very similar to KNN, K nearest neighbor. If you assume that K is the number of theta and the metric that you use is the distance between the simulation. I will come back to this later. So actually, so what we called, I mean, when we say we is astronomers or people more in machine learning thing called KNN, the statistician will call it approximate Bayesian computation, which englobes also the way you compute your model and your simulation. So I will come back to this. So For the ABC, I will ask the question, which is the best SFH to use for a given galaxy? Should I use the tau delayed, very simple galaxy, or should I add this additional degree of freedom to model the SED of my galaxy, which is a complicated question, because the more degree of freedom you add, the impact, is it necessary to add this degree of freedom to have the best result possible? So it's not completely easy to answer. So basically what we do is, for each simulated galaxy, we choose the SFH model, the tau delayed or the delayed plus the flexibility. And then in a uniform distribution of all SED parameters, which are the age of the galaxy, the tau for the tau delayed, the tau main population, the age of the flexibility, the strength of the flexibility, you have also the attenuation, the infrared properties, etc. You randomly choose different SEDs to build your sample of a simulated galaxy. So you build the resulting SED, and you convolve the SED into different set of filters. Here we use from UV to mid-infrared filters. And then, as I explained before, you compute the distance between the summary statistic of the simulated SED and the one of the real data. So this last part is really what we call the KNN part of the ABC method. ABC englobing the point 1, 2, 3, 4, and how you build your SED parameter from a different distribution. And this is why I used SED modeling, is that because we have a clear view of the range that should be used for the age, for the attenuation, etc., for the properties. So you can see here a sketch for what we done, what I just said, and then we generalize ABC to other algorithms, because we noticed that KNN is not the most efficient. So we will try different algorithm, in machine learning algorithm, to find something that is faster and more efficient than KNN. So I will show the results. So how we proceed? We generate N simulation. So in our case, it was 4 million sources. We summarize all the simulated data set, photometric SED, and we store them into a catalog. And this catalog is used for the training. So 19% of the galaxies are used for training, 5% are used for validation, and 5% for the test catalog. And then in addition, we have 30,000 sources just to compare with a more traditional result with a more traditional SED fitting method. So for each machine learning method that I will present, we tried we applied this catalog, and we choose them by comparing their classification error. And at the end, the ABC method will return the probability that a galaxy had a recent variation of star formation history computed with the best machine learning method. So at the end, we end up with a probability. So there are some limitations in this method that are just due to lack of research, not lack of research, but we need more research in terms of from the statistical approach, because at the moment it's very difficult first to handle different Steinhart to noise ratio between your data point. So if you have a flux that has an SNR above 10, but in the other band you have an SNR of 2, it's very difficult to take this into account in your work. And then there is the problem of the missing data, and you can find two kinds of missing data. First, on the left, if you have a galaxy that is not observed in one band, so you can imagine a galaxy in the blue frame, but which is not observed in the green frame, or vice versa. And this is not a physical information, it's just a lack of information. But then you can have also a galaxy that is not detected in one band. And this is in a physical information, because it means that your galaxy is weaker than a given flux. So this should be used ideally in your method. So these 2 points we required some more study from the statistical part to be able to match actually the problematic that we have in astrophysics. So since what we did is the proof of concept study, we had very drastic constraints. So we decided that all galaxies should be detected in all bands. So that means that we had to reduce a bit the number of bands, photometric bands we need to use, with a signal to noise ratio above 10. So an ideal case for this study. So should be okay. So here are the results. So on the left top left table, you can see all the machine learning algorithm we tested and the error rate we obtained. And the best results were obtained with XGBoost, so something close to 21%. And also XGBoost provided some results that are very fast, like for the whole sample. So it was 200,000 sources. So it provided some results in less than 1 second, when KNN provided in less than 1 minute. So 1 minute is not a lot, but here we had something very, very fast. And as a comparison, we also tested with the more traditional SED fitting with Ciesla. So before going to this statistical approach, I used a method based on the Bayesian information criteria, where I did two SED fitting run, one with the tau delayed SFH and one with the flexibility at the end, and I compared the quality of the fits. And this was done comparing the chi-square and taking into account the number of degree of freedom, which is different between the two SFH. When we have the flexibility, you have the age of the flexibility and the RSFR parameter, which provide two additional degree of freedom. But the problem is that in SED fitting, it's very difficult to measure accurately the number of the degree of freedom. This is why we went to this statistical approach. But if I compare with the method I used in 2019, it's a green line you can see on the right plot. You can see that clearly with our statistical approach, with the ABC, we can do way better. We will at best at 29% error rate, and we went down to 21%. So this is a good improvement. So here are the results. So I will try to guide you through this, just to remind you that the RSFR parameter is the SFR now observed from your galaxy, divided by the SFR before the flexibility, so before the quenching or before the starburst. So if you look at the green panel, you have on the x-axis the probability that a galaxy experienced a recent variation of star formation history. And on the y-axis, you have this RSFR parameter. So for positive value, you have a starburst, and for negative value, you have a quenching of star formation activity. So if you look at the bottom panel, so this is just a projection on the x-axis, you have the distribution of the probability of your test sample. So if it worked perfectly well, you would have a peak at 1 for galaxies with the flexibility and a peak at 0 for galaxies with no flexibility. This is how your trained sample was built. Half of the galaxy used the SFH with flexibility, and the other half didn't. So first, what you can notice is that there is no galaxies on the 0 point. It's around the 0.2 probability, and this is normal because the tau delayed SFH is a particular case of the SFH flexibility, is the case where RSFR equal 1, no quenching, no starburst. So the two models are nested, and this is what we expect for this kind of models. And you can see there is a tail in the distribution, and then you have all the galaxies in the with a probability of 1. And if you look on the right panels, so this is the projection on the y-axis. So you see the distribution of the galaxy given their RSFR, and this is the numbers. And you can see that if your RSFR is above 10 or below 0.1, so 1 order of magnitude from one side and the other, you recover perfectly well the fact that they had a change of activity. So if your star formation rate now is 10 times or 0.1 the star formation rate before the flexibility, you know that there was this kind of variation. However, if you have something smaller than something weaker in terms of variability, then it becomes very difficult to point it out, and the delayed normal delayed SFH is valid. So this gives you the sensitivity of your method. So now we applied this method on real data. This was on simulation. And when we want statistics in extragalactic, we use Cosmos, the Cosmos field. And we make a very simple selection because we wanted to try the method. So we use galaxies with redshift between 0.1 and 1, and with a stellar mass above 8.5. And as I said earlier, the signal to noise ratio above 10 in a set of photometric bands that have the broadband photometric, and we use galaxies that are detected in all of these bands. So basically is UV, GHK, and the very common photometric band of Cosmos. And this is the results. This is the distribution of the probability for our sample of 42,000 galaxies. And what you can see is that the majority of galaxies have a probability that is lower than 0.5. This means that for all these galaxies, the tau delayed star formation history is perfectly fine to model the SCD and recover the properties. So for these galaxies, if there is a variation of star formation activity, we cannot pinpoint it with the method we use here. It's something very weak, and then maybe spectroscopy is needed. But you still have galaxies with probability above 0.9. So the shades of green give you the Jeffrey scale, which is actually an interpretation of the probability. So I give you the color code on the right. And you can select these galaxies on the right, which are galaxies for which there was a strong starburst or a quenching. So these are the galaxies that are the most interesting for me. So I selected this galaxy, but what the ABC method told me is that there is a high probability that a strong variation happens, but it didn't tell me if it's a starburst or a quenching. So then I used traditional SCD fitting and selected a quenched galaxy. I wanted to see galaxy rapidly quenched, recently rapidly quenched. And you have two examples here. I put the SCD on the left and on the right. And just to check that our method provided something that is realistic, you can see in the bottom the optical spectrum of these two candidates, and you can see that there is no strong emission line that could be attributed to star formation activity. So we were confident that our method indeed pinpoint some galaxies that were quenched. So this was a good thing. And then we played the game to try to recover the position of this quenched galaxy in the stellar mass and star formation rate diagram before the quenching happened. So how we can do that? On the top left panel, I just show you some example of star formation history, which is very simple, but just to show you that if you have the SFR now, and you have the R SFR parameter, and you have a good determination of your age of flexibility when the quenching happened, you can try to recover the SFR before the quenching happened. And we can do that also because we did some simulation in previous work when we show it's the bottom left panel that we could manage to recover quite well the RSFR parameter for this type of galaxy. You see it was a a simulation from which we added noise, and we tried to recover the RSFR, so something very classical. And you can see that the SFR input and the SFR output are very close to the one-to-one relationship. So we were confident that we could have a good determination of the SFR before the quenching happened. And you can see on the right panel, for some Cosmos galaxies, some quenched candidates. So it's not a study that meant to be complete, but I really wanted to have the base case candidate. And you can see that we could put them back on the main sequence before they quenched. So this was a first attempt to try to recover the movement of the galaxy in the scatter of the main sequence. And then I went to do something a bit, I tried to dig a bit more and use also the long-term star formation history and try to recover the infrared luminosity of these galaxies before the quenching happened. So also it's based on assumption that the fact that if the galaxy did not quench, they should share a similar property to galaxies with a similar redshift or stellar mass, and etc. And you can see on the right panel, you can try to see with the in the x-axis, this is the age when the quenching happened, and the y-axis, the ratio between the infrared luminosity now and the infrared luminosity before the quenching. And you can try to see how the infrared luminosity decreased since the quenching. So there is a sample from Cosmos and also from a local galaxies in blue, in the square blue. And I wanted also to completely different, but just to show you another example of an ABC application, just to show that I use it for star formation history, but it's very easy to change the question and just apply it to another problem. So the other problem was, is there an AGN emission that contribute to my SED of galaxies? So it's a completely different thing, but the philosophy is the same. You have on the top left panel the infrared SED of the galaxy, and I increased the contribution of the AGN from blue to dark red. And I used like 4 bands because it was a study made for Spica, because before it was abandoned by ESA. So we only had 4 bands in infrared, and I wanted to see is it possible to constrain the contribution of an AGN, an active galactic nuclei, to the SED of my galaxy, just using ABC. If I use SED fitting, it's the bottom left panel. You can see several problems. So the true contribution of the AGN is in the x-axis, and the y-axis is the estimated from SED fitting. And you can see that there is first a bias. If you have galaxies with no AGN contributions, so the 0 point, you can see that the SED fitting will give you, in any case, a contribution which is of the order of 10%. So first, this is a problem. It means that you will have 10% contribution of the AGN, even if it's not true. And then you can see that if it was very well constrained, it would be on the dark line, the dark black solid line. And you can see that from the red point that there is a plateau at high value, and we are not close to the black line. So it's complicated with SED fitting. So I use the ABC method. In this case, I didn't use a XGBoost, but random forest. It was perfectly fine to use that. And first, you can see that when your galaxy has no contribution of an AGN, so the 0 point on the x-axis, you have a success rate which is more than 90%. So only this provides you very good results compared to traditional SED fitting. And then you see with the stars, the increase of success rate. Of course, when you have a very high fraction of 50% of the contribution of the AGN to the total infrared luminosity, of course, it's very easy to pinpoint it, and you're close to 100% of success rate. And the lower the fraction, the lower the success rate. But here we have something that basically is very efficient compared to SED fitting. So this was another example of a ABC application. You can ask another question and try to apply it. And if I have time, I'm not sure if I'm not too long, but I will present some other approaches in the literature to constrain the star formation history of galaxies. Mine was just one. And first, I found this study using convolutional neural network. So it's a recent study from 2019. You can see on the left the plot that I show you 100 times, the star formation rate as a function of stellar mass. And they use a sample, two samples of simulated galaxies. So the orange are Eagle galaxies and in blue, the Illustris galaxies. And what they wanted to do, because they have access to all, of course, the properties of this simulated galaxy, is to use synthetic galaxy spectra to recover high resolution star formation histories. And here are the results on the right panel. These are 6 different examples. The blue lines are the true star formation history from the simulation. And the red lines is what it's what they recover. So you can see that there are different results with different quality. But first, what we need to be added here is that they had, for the synthetic galaxy spectra, they had to apply some attenuation. So attenuation is something that complicates things every time in SED modeling. So it can explain also some differences that you can see between their results and the true one. But this is very interesting because you can imagine then using CNN and machine learning to recover the star formation history of your galaxies, and then use that as input in your SED modeling part. And then you break some degeneracies with the application of attenuation, and you have more precision in your physical properties. So this is an approach that is quite interesting. And the other one I wanted to develop a bit more is the self-organizing maps, the SOM. So here the approach is completely different. So you have a sample of galaxies, which are the purple points. And you have some flux, and you compute the colors of the flux. So the 3 dimension that you see here, it's an example of 3 colors that you will have. So each galaxy is represented by the vector of its colors. And what the SOM will do, it will sort the galaxy from their colors, reduce the dimensionality, while preserving the order and how they were sorted. So this is a sketch, and in result, what you obtain is this kind of map on the left. So you can see here the axis D1 and D2. So if I come back here, they have this hyperplane that you can see in black. And the color code here is the redshift from the Horizon AGN. So they did this study from simulation. So they used the Horizon AGN. And they use 9 colors that I list at the bottom left side of the slide. And you can see how galaxies are sorted or placed on this SOM. And just to come back also to a different method to measure star formation rate from using machine learning, they use this method. This is on the right figure that you can see to obtain the star formation rate. So the idea here is that each galaxies that are in the same panel, so the same pixel, sorry, they share the same properties. So if you point 1 pixel, you will have galaxies with the same star formation rate. This is what this is one of their results. And you can see here how it's placed on the SOM. And they try to use that and calibrate their work to use it as a star formation rate estimator. But to go a bit further, because I'm focused on the star formation history, you can also see if your galaxies that share the same pixel also share the same star formation history. So if you look at 1 pixel here, for instance, and you have a closer look at the spectra of the galaxies in the same pixel, you see that they have very similar spectra, but also very similar star formation history. So this is the right panel. And so this is one example. Another example here, you have a different spectra, but here again, the galaxies in the same pixel seem to share the same kind of star formation history. And here is the last is the last example. So this is also a very promising method to recover the full star formation history of your galaxy, and try to see from one map galaxies that share the same properties and recover the history. So this is my summary. I wanted to present how we used ABC to perform SFH model choice in aiming to recover the recent movement of the galaxies, the recent evolution, and understand their evolutionary path. It allows us to build a sample of rapidly quenched candidates that now we can study and try to understand what are the mechanisms that produce this rapid quenching. We also try to recover past properties, which is quite interesting to do some archaeology on this kind of galaxy. I wanted to show so that very easily the ABC method can be applied to a completely different question. And then I showed some different methods. So more and more machine learning approaches to derive physical properties of galaxy. These are recent work, 2019, 2020. So this is something very exciting and promising because it's completely under development and it's completely new. And it will go, of course, from physical properties, you go easily to star formation history. So we will find more and more study trying to recover the full history of the galaxies. Thank you.
Thank you, Laure. So do you have questions? A clap from David. Hello, David. Question.
Actually, I was just applauding.
Yes.
Thank you.
but I also have questions. It is absolutely fascinating. I think it can change completely the way that we are analyzing galaxy catalogs based on, say, magnitude. So my question is, it's perhaps too early to ask, but have you thought about what will be the minimum number of filters and their locations in wavelength in order to, say, to reproduce the stochasticity of the star formation rate history?
Okay.
Right, I'm thinking on terms of observations. Can we decide the minimum set of filters that will give us the maximum amount of information?
Okay, so for the study that I just presented now, it was not that much because since we needed to have all galaxies detected in all filters, we had to reduce, and we had like the 4-Spitzer, the IREX filters, and you have also some, when you need to probe some UV, some near infrared, some mid infrared, and a couple of them in between UV and near infrared. And actually we had like 10 filters, and we computed colors because classification method doesn't like absolute values. So we computed colors, and we had like 10, a bit more than 10 filters. And after that, you can increase. If you want to have something more accurate, then you add your filters, but also you can have, for instance, the flux of an emission line of H alpha or something like this, and then you will increase your accuracy. So the minimum, I would say, is maybe what I showed here with like from UV to mid infrared, like something like between 8-10 filters. It's quite good. But then if you want something more accurate, the more is the best. But of course, there are some filters. I mean, if you have something very close in terms of wavelengths, it won't change a lot the error rate or the success rate. So it's maybe the diversity of information. So maybe one can add emission lines or stuff like that to improve the accuracy.
Right, because I suspect that we need a filter, say, below the Balmer break.
Yeah, sure.
And another one somewhere in the UV, right? To have the
yes, when I say
star formation. So if you remove the UV filter, that would be a disaster, right?
Yeah,
so,
yes, completely. Yes, when I say UV, for me, the mandatory ones are UV near infrared, of course, but also I noticed when I did the study from LCD fitting that you need some filters in between UV and near infrared, because you will have this what I call green population of stars, something intermediate, and you need the intermediate emission of the stars to recover well if it's a recent quenching or it's something, to distinguish between a galaxy that formed star normally and then quenched from a galaxy that was passive and then just because of a merger have some UV emission due to recent merger or something like this.
Right.
So,
yeah.
Well.
All right, thank you.
If I could add a question or a comment related to this discussion, maybe it would be interesting also to, I mean, to know the best filter that would catch the larger range of redshifts. In fact, because your best filter will obviously depend on redshift you want to tackle. I mean, the redshift range. And maybe by optimizing the choice of the bands, you can have the largest range of redshift for which you would gather the information.
Yeah, exactly, because this is one of the limitations maybe I didn't mention, but we reduced the range of redshift for our study because we didn't want to go into this redshift problem because it was something quite new, but this is also something to be developed from the statistical side. So the missing data, the signal to noise ratio, and also the redshift. Ideally, it would be something that could do everything, but we didn't test. We said, okay, just at the moment, just try to do something robust and just see if it works first. And then, of course, yes, we need to handle how redshift, because it will affect everything. Then you need to recalibrate or something. So something not clear now, but it's definitely an axe of improvement of development even. Yeah,
I was more thinking in the rest frame to make things simpler.
Yeah. When I gave the band, I said in rest frame, but redshift is a problem actually.
Yes. So another question: do you have any plans to implement upper limits or non-detections?
So in SCD fitting, yes. In our method, no. Actually, I discussed with the statistician people involved here. They think it will take like they said we will need a PhD to do that. They need it's quite something. They said that the signal to noise ratio problem is quite easy to implement, but the missing data, because you will have some different reason why the data is missing, as I showed. It requires some developments. So actually, it's not. It's something to be developed too.
Well, that would be extremely useful.
Yeah, because these are, I mean, redshift, signal to noise ratio, and missing data. They are key problems of our field. So
right,
we need something here. Yeah.
I had another question about. I mean, if I understood correctly, you can recover the historic path for the galaxy. And my question was about how much this would be degenerated. I mean, when you find some good path, do you catch? I mean, do you have a range of possible path at the end?
So here, what I did is, as a first step, I was very, very selective in my candidates. So I use candidates with like a star formation rate, which is quasi zero now. So I know they are quenched. And I used a delayed, also a criteria on the long-term star formation history. I wanted to not be polluted, if I can say, by passive galaxies. So I asked for something that was quite constant and then was reduced, and I just focused on quenched galaxies. So I was very careful, and also I used the spectroscopy to check when it was available, and etc. But if I want to do something more statistical, like I unleash all the criteria and just build back the starburst, quenching, rejuvenation, and everything, I would need to be careful here just to try to see if I can go back in this thing. I was very restrictive, but for me, this is my future work is actually doing something more statistical to try to release a bit the criteria and try to see if it still works. And also I spent quite some time looking at the impact of attenuation, the different attenuation laws on this. So it's a huge work, but I like to do that. I mean, it's the future development I would do.
Okay, this is related to the question I had, because at some point you showed a quenched SCD for which you verified, I mean, the galaxy was like that. I mean, it's true SCD. And so you don't have an example of the how to say, a quick change, like with a starburst, a recent starburst.
This is something like I'm actually,
if you would like to
yeah,
if you would like to grab, sorry, the connection is not, my connection is
yeah,
not very good. Something like an elliptical galaxy that all of a sudden would have a face a starburst, and then you would find, all stellar population in the SCD, but also tracers of recent star formation, which is the kind of example you would like to verify as well.
Exactly, and it's something. I mean, now I have this sample, so the ABC method gave me this sample, and for the first study, I just said, okay, I will focus on the quenched, and now I mean, I have all these galaxies, so I would like to look for this rejuvenation from passive with some UV, some young population. I would like to look at starburst. So also I'm now using for a project that I'm just starting. I'm using a Muse-wide because I have a spectroscopy, and I am applying this method, and then I will have more information in terms of spectroscopy. And also I looked at I would like to focus now on starburst, and also I would like to pinpoint starburst and see if I can say something about them coming back to the main sequence or quenching completely. This is the question it was, I think, the red path on my plot. So if I have the starburst, will it come back on the main sequence, or will it be completely quenched and go directly to the passive galaxies? So it's the key question I would like also to answer. But this is very exciting with this method because I have this sample, and now I can look at all of them. Why do they have this flexibility, and what is it needed? So first I did the quenched one, and now I want to look at the other ones.
And I have a very last question. You showed, I mean, at the very beginning of the talk, you raised the question of the scatter of this the main sequence, which is something that we know is very interesting. And at the very end, you showed that you could reconstruct the history and compare the previous properties of the galaxy. And you show from one point that it was inside the scatter. I mean, I don't remember which slide it was, but yes, maybe you can show it.
Is it the one?
Yes, this one. You see that more or less it's close to the scatter. I mean, have you checked that for the full sample, your previous properties of your galaxies, where would they stand in this compared to the scatter we observed? And if in terms of probability, I mean, you have the age, so you know if in a time scale, in a given time scale, this can happen or not. And then maybe derive something of consistency or inconsistency with the scatter of this SCD over a given range of bin of redshift, or let's say time scale. You know, if you reduce the bin in redshift or the time scale, you can see if those objects, may oscillate inside this main sequence.
Yeah, so I didn't go this far in terms of testing the scatter and everything. What I did is just checking that the past properties of my galaxy were consistent with the properties of galaxy with similar redshift and stellar mass. So just to check if I was not off completely. So this is the first check that I made. And actually, this is completely my research plan. I mean, it's to be able to recover this path and see if it's consistent in the scatter, and try to see the movement back of the galaxies. This is completely what I want to do. So since it's a bit recent, I didn't have time to go further than that. But it's what I'm doing now, and I would definitely test that. It's a good idea.
Okay, because if I understand correctly, since you focused on the quenched galaxies, if you do that with a sample you have, you would have a cloud of well, you would need to study the full sample if you would like to see the scatter, because you would need to also grab the new starbursts and everything.
Yes, and I would need to be complete. And since I put very harsh criteria from the beginning, from the ABC method, and also when I selected my candidate, I'm afraid I won't be able to give some statistical answers. I need to first fix all these criteria that I put just to have a study that is working, and so develop the ABC method. And when I have that, and I can produce a statistical method, yeah, now I would take all this the starburst, the quench, and make everything move and see if I'm going back, the scatter that I found is still consistent. Yes, it's a completely it's a good idea, and it's completely something to be done. Yeah.
Thank you very much. Okay, I think we can stop now. Merci beaucoup.
Merci à vous. Hein. J'étais très contente de donner ce séminaire. C'était
super intéressant.
Merci beaucoup en tout cas.
Écoutez, à bientôt. On discutait avec Samuel.